Hey, physics friends. Welcome to 4.4, which I've entitled Putting It Into Practice. What I did, I picked 4 problems from various parts of Chapter 4, and I put them, and I'm going to be doing some example problems, just actually solving some problems using numbers, putting all these concepts and overarching themes into practice. So let's get started. I'm going to start with number 67. It says you place a 7.50 kilogram television on a spring scale. If the scale reads 78.4 newtons, what is the acceleration due to gravity at that location? So what I'm going to do, I know 7.50 is a mass, so the mass is 7.50 kilograms. It reads 78.4, that's a force. 78.4 newtons. What is the acceleration? So the acceleration equals question mark. So what I'm going to do, think to myself, I wonder if there's an equation that involves all of these things, and there is. It's this. I know my force is 78.4. I know that my mass is 7.50. I'm looking for my acceleration. Now, I know that I write the net force, and that's the only force that's acting on this right now. Even though there's a spring, it's being pulled down by gravity, and there's a normal supporting force on this thing. So I'm looking for gravity. So to find my force of, well, I called it the net force, but I could also say the force of gravity equals the mass times the acceleration. So I'm expecting it to be around 9.80. So let's just give it a look-see here. So 78.4 divided by 7.50 comes out to 10.5. So my acceleration due to gravity at this place, 10.5 meters per second squared. So we're underneath quite a bit more gravity than we normally are. Number 69, my second example. Assume that a scale is in an elevator on Earth. What force would the scale exert on a 53 kilogram person standing on it during the following situations? Letter A, the elevator moves up at a constant speed. So when you're in a scale, so here's you standing on a scale in an elevator, you have a certain amount of weight. And we can figure out what that is because you take your mass, which is 53 kilograms, and you multiply by 9.80, and then you end up with 520. So the force of gravity on you is 520 newtons. Now the question is, which way are you accelerating? Because if you accelerate up, that means that the upward force of the normal force, what the scale reads, is going to be bigger. If you're going to accelerate down, that means that you're going to be smaller. And if you're not accelerating, then they're going to be the same, which is what part A is. Part A is there's no acceleration. So that means that the upward force of the normal is the exact same. So 520 newtons. And the scale is going to read exactly what the normal force is. Part B, it slows while moving up. When you're slowing down while moving up, that means your acceleration is in this direction, which also is going to mean that my normal force is a lot smaller than that. So I'm slowing at 2 meters per second squared. So I'm going to use my equation again. My net force is going to be my up force, which is the normal force, minus my down force, which is gravity. I don't know my normal force. I know that my gravitational force is 520, my mass is 53, and my acceleration, I'm accelerating in this in the downward direction, which is negative. So it's going to be negative 2. So when I do this, I take 53 times negative 2, and then I'm going to add to it 520, and I get 414. So my normal force in this case, 414 newtons. And that makes sense that it's smaller than 520. Part C, it speeds up while moving down. Speeding up while moving down means that you're still accelerating in this direction, so you're going to get the exact same thing. Part C, 414 newtons. Because it doesn't matter which direction you're moving, all it matters is which way you're accelerating. And I'm accelerating down, so there you go. Part D, it moves down at a constant speed. So constant speed, no acceleration. It's going to be 520 newtons. And part E, it slows to a stop while moving down. So if you're going down and slowing down, that means that your acceleration is in this direction. And if your acceleration is in this direction, that means your normal force is going to be very big. So we'll run through our equation again. So we'll say the net force equals the mass times the acceleration. My net force is the normal force minus the force of gravity. There's only two forces acting here. My normal force is unknown. My force of gravity is still 520. My mass is still 53, but now my acceleration is a positive 2. So when I take 53 times 2, and then I'm going to add over 520, so I add to it 520, it comes out to 626. Like that. So I have a larger normal force, which makes sense. Number 74, I've got a race car, and it's got a mass of 710 kilograms. So maybe I'll draw a picture for this one. Well, that's a terrible car. It starts from rest, so if it's 710 kilograms, there's a force of gravity acting on this thing. 710 times 9.8, 6958. There's a normal force supporting it. It starts from rest and it's accelerating, so there's some force, we'll just call it the engine, accelerating it. The car starts from rest, so I know that its initial velocity is 0. And it travels 40 meters, so the distance is 40 meters in 3 seconds. That's the time. The car is uniformly accelerated the entire time. What is the net force? So my net force is going to be my mass times my acceleration. These two forces cancel each other out, so my net force is actually the force of the engine. We're going to ignore any backwards forces by friction because they don't make any mention of friction or drag, so you're just going to ignore that one. Even though there is a force back there that would subtract from the engine, don't worry about it right now. My engine force is unknown. My mass is 710. And my acceleration I'm going to pull from all these things. I think that I'm going to use the one that doesn't use VF, which is this guy. So my distance is 40. Starts from rest. I don't know the acceleration, and the time is 3. So I'm going to take 40, and I'm going to multiply the 2 over. So 40 times 2. And then I'm going to divide it by 9. And that's going to give me 8.88. So my acceleration comes out to 8.88. That's pretty good. Almost 1 g. So to figure out the force of my engine, I just multiply that 710 times this number. And I get 6,300 newtons. My last example, a weather balloon. I've got the instruments are attached to the weather balloon in the below figure. They have a mass of 5 kilograms, and the balloon is released, and it exerts an upward force of 98 newtons. Okay. What is the acceleration? So, just to get my picture straight here, I've got a balloon, and there's an upward force, a buoyant force, that's what we call this, of 98 newtons. And then there's a downward force of gravity. It's 5 times 9.8, that comes out to 49. So this thing's totally going to accelerate in the upward direction because there's an imbalance of force here. So to figure out my acceleration, I take my net force, which is the buoyant force, minus, because I'm going to say upward is positive, minus my force of gravity. The buoyant force is 98 minus 49. The mass was 5 and the acceleration is unknown. So 98 minus 49, I think, is just 49. So I take 49 divided by 5. It's probably like 9 point something, 9.9. 9.8. Well, that's weird. It's going to accelerate that way at 9.8, so it's almost like a reverse gravity. Part B says, after the balloon has accelerated for 10 seconds, the instruments are released. What is the velocity of the instruments at their release? Okay, so the initial velocity, they're starting from rest. Their acceleration is 9.80 in this direction, and you're releasing them for 10 seconds. How fast are they going? So you're going to use this equation, VF equals VI plus AT. This is 0. The acceleration is 9.80, and the time is 10. So that just comes out to 98 meters per second. Part C, what net force acts on the instruments after their release? So after these instruments are released, what net force is acting on them? Well, they're no longer being pulled up by the buoyant force. So the only force acting on them is gravity. So part C says, what net force acts on the instruments? The net force is gravity, and it is 49 newtons down. And part D, when does the direction of the instrument's velocity first become downward? Ooh. When do they start moving downward? So you know what I'm going to do? I'm going to say that their initial velocity is 98 newtons meters per second in this direction. So right when it lets go. So this balloon is taking this thing up, and then it cuts the cord, and these things go up, and then they stop and they come back down. So initially their velocity is 98. I'm going to say, when is it 0? So when is it 0? I know that its acceleration is in this direction, downward at 9.8. So we're looking for the time. So VF equals VI plus AT. Final velocity 0, initial velocity 98, negative 9.80 t. So t comes out to be 10 seconds. Pretty nice. So there you have it, kind of putting all together, knowing which forces are where and how big they are. Putting some numbers finally to some of these questions.